Units of pressure come in two forms: force per area and length. So 1 atmosphere of pressure can be 14.7 psi, pounds per square inch, which is force per area, or it can be 10 meters of water or 76 centimeters of mercury. Here's how to derive the formula to convert back and forth between force per area and length. Pause the video if you want to figure it out for yourself. First off, quick tangent because I think this is interesting. If you have a tire with 55 psi in it, that's 55 pounds per square inch. That could be absolute pressure. That pressure is pushing down on your tire pressure gauge right there, telling you the pressure that's in your tire. But then you also have 1 atmosphere of pressure pushing back, which is 15 psi. 55 psi minus 15 psi gives you 40 psi as your gauge pressure. So you can take your psi absolute minus your atmospheric pressure to get your psi gauge pressure. And next page. You can have a tube full of water or a tower full of water that is open at the bottom, and that water will not spill out if that open part at the bottom is underneath a pool of water, and that pool of water is open to the atmosphere. And this is because the atmosphere is creating a force pushing that water down, trying to push that water up into the tube. At the same time, all of that water inside of the tube is creating force pushing down, trying to push this water out of the tube. The atmospheric pressure pushing down on that is 15 psi, and it will push that water level up to 1,000 centimeters and cannot push the water column any higher than that. If you were to pour extra water in this tube right here, say from the top, the extra weight of that water would push the water down and out and into that pool of water right there. This is how you can capture gases if you want to do electrolysis and bubble up pure O2 and H2 to collect at the top. I've read on Google that doesn't work on an industrial scale because you end up with too much water vapor at the top, but not my field, just something I thought was interesting. This is also why you cannot suck water up through a straw greater than 1,000 centimeters or 10 meters. Because when you're creating a sucking action there, you're creating a vacuum and allowing the atmospheric pressure to push this water down and up into the tube. But after that water gets to about 10 meters high, that the weight of the water becomes too massive and starts pushing back down and wanting to push that water out of that tube and into the pool of water. Another way to say this is the force of the water pressure inside of the tube is balanced with the force of the air pressure outside of the tube up until that water height gets to about 10 meters. Mercury is about 5 times denser or 5 times heavier, so that column height only needs to be about 1/5 of the height to exert the same amount of force pushing down. Here's an interesting thought. What if we increase the size of this pool right here so we have more surface area for the atmosphere to push down on? Would that increase the amount of force pushing the water down here, thus pushing water up into the tube, and possibly make the water level in that tube go higher? Well, you will have more overall force pushing down on this surface area of water right here, trying to push water up into the tube. The water level in that tube is also creating a force that comes down and exerts evenly over this pool of water, pushing up to counteract the atmosphere. So the amount of surface area you have on this pool of water that's exposed to the atmosphere doesn't matter. So now we understand how pressure, which is typically measured as force per area, can actually be turned into a length. Let's look at how to convert back and forth between length and force per area. If you have one block of water right here that is 1 centimeter in all directions, that'll be 1 cubic centimeter. That will weigh 1 gram. If you have a tower of blocks right here, or a column of blocks, make your base 1 unit by 1 unit. In this case, I'll do 1 centimeter by 1 centimeter. Make the height whatever you want. In this case, I'll make it 4 centimeters. Now maybe you can imagine if you're at the very bottom here at this 4 centimeter column of water, you will have 4 grams of weight pushing down on you because each little block right there of 1 cubic centimeter weighs 1 gram. So those 4 grams from those 4 blocks are pushing down on an area that is 1 square centimeter. So for our pressure at the bottom, we have 4 grams per square centimeter. Here's the formula to convert back and forth between height of your water column or height of your mercury column and force per area. Height times density equals your pressure. So height, in this case, I will use centimeters. Density will be grams per cubic centimeter. The top centimeter will cancel out. The bottom centimeter will have an exponent that goes from 3 down to 2. So you end up with grams per square centimeter. I'm leaving this as a kgf equivalent or kilograms of force equivalent and not turning that into newtons, since most people are much more familiar with kilograms or grams compared to newtons. On the next page, I will use this height times density equals pressure formula to convert the height of water and mercury into a pressure of force per area. Using the formula of height times density equals pressure, I'll start with water. We can take the height of water under 1 atmosphere of pressure, which would be about 1,000 centimeters or 10 meters. Multiply that by the density of water and you'll get about 1,000 grams per square centimeter of pressure. Notice what we've done here is converted a linear unit of length or height into force per area. Next, I will convert force per area into height. We can rearrange this equation to pressure divided by density equals height. We can take that same pressure of about 1,000 grams per square centimeter, divide it by the density of mercury metal, and we'll end up with 76 centimeters, which is the height that mercury goes up in a tube under atmospheric pressure. Notice what the units do here. Gram divided by gram will cancel. And this cubic centimeter is in the denominator of a denominator, which means it will go up to the numerator. This square centimeter is in the denominator, so you just end up with centimeters as your unit, as the height.